Hello, everybody. Welcome back. Welcome to your first lesson of Calc BC, the third year, if you've had me for 3 years, 2 years so far, of the entire system that hopefully gets us to the end of all of the calculus stuff. A lot of it we learned last year, and some new stuff that will be new this year. So, starting off, the lesson today is just going to deal quickly with domain and then a couple of other refreshers that I will get into. But domain's the big one. It's a good place to start. Domain is going to be one of those things we pay a little more attention to this year, on top of things like continuity and differentiability and those other more technical side of math. Now we have to pay a little more attention to them than we did in Calc AB. So this one's not going to be too long today. I just want to talk about domain. What is domain? So domain are basically the x values that can be, and I'm going to put it this way, plugged in to a function and yield an output. So when you plug it in, you get something out. If you plug in 4 to whatever the function is and you get out a number 7, bam, 4 is in the domain of the function. If you plug in 4 and you get undefined, then 4 is not in the domain of the function. That's really what domain is all about. So it talks about which set of values we can plug in and which ones we can't. So I'm going to do a couple of examples to remind you how this works. The most common ones, the first one, is a function that looks like this. F of x equals square root of x minus 5. When we're first learning about domain, we talk about these types of functions because these are ones that have a very clearly defined domain and very clear values that you just can't plug in. This is a radical function. And when you have a radical function, you cannot plug in values that give negative answers. You can't have a negative output because then you'd have the square root of a negative number, and those are DNE, do not exist, undefined, when we are dealing with calculus. So how do you go about, if you don't know how to work the problem, how do you go about finding what values work? Well, you can always try just plugging numbers in and seeing what work and what don't. But when you're dealing with a radical function, there's a better way. You can look at the inside of the radical and set it equal to 0 and solve for x. This gives you what I call the boundary point. It tells you where we start having issues, where the domain starts to exist and stops to exist. So you could put it on a number line. And then just like we did with the first derivative test last year, you can test points around 5 and see which ones work and which ones don't. So we're going to start by plugging in something bigger than 5, like 6. And if you plug in 6 to the original function, you get 1. And the square root of 1 is 1. So this area works. So that is values bigger than 5 are in the domain of this function. But what if you plug in something less than 5, like 4? Well, plug in 4, you get the square root of negative 1, and that does not work. So we would say 4 is not in the domain of this function. And then the third thing, in this case, you need to actually test 5 itself. Sometimes the boundary point will be in the function, and other times it'll be in the domain of the function, and sometimes it won't. So when you plug in 5, 5 minus 5 is 0, and the square root of 0 is 0, which does work. You can have the square root of 0, no problem. So a lot of times, if I was to graph this on a number line, kind of back we did in accelerated integrated 3, when we were solving inequalities, it would look like this. And the number line is not the answer. I need you to state the answer. So there's 2 ways you could do this. You could say x is greater than or equal to 5. That's one way. That's using inequalities. That's fine, but there's a better way. The way I prefer is using interval notation. Interval notation is actually really nice when you have the number line. Use the number line to set up your interval. So it looks like this. 5 is the boundary point. 5 worked. So we put a bracket on 5 because if it's included in the domain, bracket means included. Comma, all the way up to the end of the interval. Well, the end of the interval goes all the way to infinity. So we put an infinity, and we always put a parentheses on infinity because infinity is not a number. We can approach infinity, but we cannot equal infinity. And that would be the domain of this function in interval notation. So I prefer interval notation. Technically, inequalities are fine, but you should get used to interval notation. All right, right, so that's the first one with a radical function. Example 2, the other common type of functions that we work with because they have issues also would be something called a rational function. So if you remember, maybe something like this. Now notice I used y equals. We'll go back and forth. Sometimes we'll use y equals to talk about functions. Sometimes we'll use function notation, f of x, g of x, h of x. Get comfortable with both. But how do we deal with a rational function? Well, if you remember from our days in accelerated integrated 3 or pre-calc, if you took pre-calc or even calc AB, it's when the denominator equals 0 that you have issues because you cannot divide by 0. So in this case, if you want to find the trouble spot, you can set the denominator equal to 0, and 5 appears to be the issue again. So you can put that on a number line, and you can test the intervals around it. Now, if you plug in 6, you get 11 over 1, which is 11, totally fine. If you plug in 4, you get 9 over -1, which is -9, also fine. So what gives? It looks like everything works in the domain of this function, but no, you need to test 5. And when you plug in 5, you get 10 over 0, undefined. So the number line for this one might work like this. So what is this saying? It's saying all values except 5 are in the domain. 5 is not included. So you can write that. You could say x is not equal to 5. That's one way. Or that would be kind of how you would do inequalities. You could say x is less than 5 or x is greater than 5. Don't say and because you can't be both at the same time. But I like interval notation, so we'll do this. We'll go negative infinity all the way up to 5 and then parentheses because 5 is not included in the domain. Union 5 to infinity. Close the parentheses. Parentheses because we are not including 5 in the domain. 5 is not in the domain of this function. Right? And that is how we deal with a rational function. We talk about when the bottom equals 0. That's where the vertical asymptotes occur. So if you want to get into stuff that we'll be doing later on again, we know that there is a vertical asymptote here. That'll be when we get back to limits again. We'll talk about vertical asymptotes all over again. All right, another example. Let's do maybe one like this. F of x equals 7x over 6x squared minus 5x minus 4. So this is a rational function because we have x's in the denominator. That means we got to figure out when the denominator equals 0. So set the denominator equal to 0. All right, we have an issue here. How on earth am I supposed to solve this equation? I know you've had all summer and we have forgot to tell how to solve equations. Well, I'm going to give you a cheat sheet guide on how to do this if you have forgotten until we start getting back into doing math again. If you forget how to solve any equation and you are at home, you do not just sit there and be sad about it. You go to your trusty Desmos. We'll get back to the graphing calculator again, but for now, let's get back to Desmos because Desmos is just super helpful to do things if we're stuck. So I don't care what you're stuck with. If you're stuck, pull up Desmos and use it because it will definitely help you out. All right, so Desmos, what's up? Let's do this. How do you solve any equation with Desmos? All you need to do is get it all to one side, meaning get all of the terms on one side and get it equal to 0. Once it's equal to 0, all you have to do is graph it. 6x squared minus 5x minus 4. How do you know how to solve it? You see where the roots are. So you find the roots of the thing you graphed. So it looks like -1/2, and this happens to be 4/3. Those are the two values that cause this to equal 0. So we could go through this, put them on a number line, and we're all set. But I really hope at this point in your math career, you know how to solve this by factoring. Factoring is going to come up this year again. It always does. So how do I like to factor? I don't do the X stuff. I just try to do a guess and check strategy. So 6, I think of 3x and 2x. 3 and 2 multiplied to 6. You could also try 6 and 1, but I don't know, I've done enough of these to know that's probably going to be 3 and 2. How do you get 4? You could do 2 and 2. But if you have 2 and 2, you can't have a common factor in one of them. So, like, for example, if 2 was here, nope, it doesn't work like that. You're never going to see that case. So I already know it's not going to be 2 and 2. It's going to have to be 4 and 1. Also, with that same logic, the 4 can't go here because then the 2 and the 4 would have a common factor of 2. So if it's going to be 4 and 1, the 1's got to be here. The 4's got to be here. So I kind of go through it and I say 3x times 1 is 3x. 4 and 2 is 8. Hey, that does make 5 as long as this is the negative 1 and this is the positive 1. Which means I get two values. I get the negative 4/3. And did I plug this into Desmos wrong? One sec. I'm curious about something. 6x squared minus 5x minus 4. Oh, yeah. No, we're good. 6x squared minus 5x. Yeah, I want it to be... Oops, that's what it was. Sorry, I had this backwards. I knew something was weird. That's why I like using Desmos. 3x and 1 is positive 3x minus 8x. We're good. Okay, so the answer is positive 4/3 and negative 1/2. Which I know because that's what Desmos was saying. That's how I knew something weird was going on. So Desmos, have it handy. If you know how to do it on your graphing calculator, remember from last year, great. But for now, getting back into this, let's just use Desmos. And we already know this is a rational function. I don't need to do the number line. All I need to remember is when you're dealing with the rational function, you're undefined at the asymptotes. So it'd be negative infinity, comma, up to the negative 1/2. And then everything between the negative 1/2 and the 4/3 is defined. Except 4/3 doesn't work, but then 4/3 to infinity does work. So that's the domain of this function. The other way you can check your answers on Desmos is you can graph these things. So let's see if I can do this quickly. Control C, Control V, 7x. Oh, look. If we're looking at the domain of this function, it looks like the thing exists all the way up to, but not at negative 1/2. And then same thing, 4/3. There's an asymptote and an asymptote. So Desmos can also help you get an indicator of how the function's domain works by seeing where the graph exists. So you should definitely utilize these tools early on to get you back in the mindset of how this all comes together. So these are the two big cases, rational functions and radical functions. Other than that, most of the time the domain is all real values. Not every time. There's definitely some other ones like piecewise functions where you can have weird things going on. But these are the ones we're limited to right now. All right, the last thing I said, some quick refreshers. Trig is coming back, and I'm going to be more mean than ever with trig this year. So last year we tried. A lot of you were okay, but we're going to get back into it. So just really quick, you need to be able to solve trig equations. So I give you one on the homework. Trig equations. Let's go through kind of a basic one. Let's deal with tangent. So how about 3 tangent x plus 3 equals 0? This is a trig equation. If you are really struggling with trig and you want to get good at this, you can do what I just showed on the last problem by going to your Desmos. Everything is on one side, so let's graph it. Oops. And let's see the values at work. Check it out. Negative pi over 4, 3 pi over 4, 7 pi over 4. Remember how this works? These are called coterminal angles. They are all the answers that technically work because when you're dealing with the unit circle and all that, you have answers that repeat. The answer we most care about would be this one though, 3 pi over 4. Negative pi over 4 is also an answer. So, doing the homework and you're struggling, check with Desmos, please. I'm going to have you do these on assessments fairly quickly because you know me, trig is important to me. All right, but how can you solve this by hand? Well, just like anything, we need to get the trig part by itself. So you can subtract the 3 over and then divide by 3. So you end up getting here. I'm going to do 2 steps in one. Now, at this point, there's two options. You either use the unit circle backwards and think, where does tangent equal -1? Or you try to get the x by itself by doing the inverse tangent on both sides. The inverse tangent, or arctangent, looks like this. Arctangent of -1. Your calculator and Desmos know what this means. So if you do arctangent, see how I spelled that? Arctangent of -1. Now look what your calculator gives you. A decimal, or a Desmos. Gives you a weird decimal. But remember, we already know the answer was 3 pi over 4. So I'm guessing that 3 pi over 4. Oh, nope, it's giving us this one. Check it out. -pi over 4. So the Desmos gives you -pi over 4 because technically when you're dealing with tangent, it's going to give you answers between -pi over 2 to pi over 2. I would take this answer too. Either of these is fine. I would also take the decimal if you have access to a calculator. I would also take arctangent of -1 if it was a free response, which we'll talk more about later. But the way I would actually prefer you to do this is to remember tangent is sine over cosine. So this is really asking, where does the sine of x over the cosine of x equal -1? Or in other words, where is sine equal to cosine? Because if you divide sine by cosine, and you have the same value, you would get 1. So on the unit circle, which we're probably going to practice the unit circle on some of these Wednesdays, sine and cosine equal each other at the 45. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So at pi over 4, sine is root 2 over 2, and cosine is root 2 over 2. So the tangent of pi over 4 is equal to 1. That's why pi over 4 is not the answer, but this one is the answer, 3 pi over 4. That's how we're getting 3 pi over 4. Now, the other answer is 7 pi over 4. But what gives? The Desmos said -pi over 4. How are they getting that? Well, what they're doing is, think of it as they're going backwards around the unit circle. So if you go 7 pi over 4 here, going the counterclockwise, that's the same as going in the reverse direction, a -pi over 4. That's that whole coterminal idea. I don't care so much about that now. More, I just want you to be able to find one of the answers, and 3 pi over 4 is definitely acceptable. But 7 pi over 4 or -pi over 4, all of those are good too. So we will practice trig again. We will practice using the unit circle again. That is going to be something because I graded the AP test and saw a lot of this trig on there. We'll talk more about that in class. But that's it for the first lesson. Domain, the homework will have 2 domain problems, one trig equation, and then one kind of an old school blast from the past. I'm going to try to include more of those on the homework too as we start getting going to see if you remember how these work. Come talk to me if you can't remember. But that's it for now. Good luck, guys. See you later.